Servus.
Marhaba.
Hola. Hello.
I'm inspired that there's so many people working to accomplish the same goal of creating a connected future.
By having students lead clubs on campus directly supported by Google developers, that's the best way to reach out to students.
It's really inspirational always to hear about members of the community who echo your values and echo your beliefs.
I've been listening more than I've been speaking, and I don't necessarily think that's a bad thing because I'm just getting all these ideas.
Google, it needs to reach a wider audience and be more relatable as a company, and I think Google is one of the brands that is very good at doing that.
Hello, everyone. Welcome to the third session of our Data Structures and Algorithms series. My name is Andriy, and I'm joined by Alexander. So, yeah, today this is like a closing session, but we'll talk about a little bit more about that in the end of the session. Today it will be all about graphs. We'll talk about what they are, how to store them, how to traverse them, things like that. So DFS, BFS algorithms. But before we actually jump into that, I want to do some housekeeping first of all. So the Think Outside the Valley YouTube channel has also its own Discord server, which I'll just quickly go over. Give me 1 second. If at any point during the session you have any questions, feel free to join this Discord server. We have a lot of channels related to different like Firebase series or Flutter series that we have also like go watch them if you're interested in those kinds of things. We have our separate Data Structures and Algorithms channel where you can ask questions and engage with us after the session if you have any questions. Yeah, just some things that you will need to do. You'll need to read through these rules. We want to keep everything, like all the conversations should be respectful, and just feel free to kind of read through the rules and put a check mark right here. This will allow you to view all the channels and access all the amazing content on the server. Yeah, so that's like, you can see the link on the screen and also in the chat. And it is very important that you kind of join these channels, because if you have questions after the sessions, please feel free to DM us. We'll kind of help out in our free time. Also, YouTube comments or any other, like if anybody's watching from Facebook or Twitter, any comments you put there, I'll try to answer in the background while Alexander will tell us everything about graphs. Yeah, that's pretty much the format of today's session. Yeah, I think we can jump straight into it. One more thing I'll mention before we start is actually we have our separate GitHub repository where we have links to slides that will be presented today and in the earlier sessions, and also links to these YouTube videos if you ever lose them. So yeah, make sure to kind of check that out. The link is on the screen. I'll drop that in the chat a bit later as well. Yeah, if you ever want to look through the code again, see the implementations of what we'll be showing today, feel free to do so. And also contribute, by the way, if you have any ideas of how to improve what we'll be showing, please submit pull requests. We're happy to look over those. All right. Yeah, let's just jump straight into it. We have a lot of things to cover, so I'll hand it over to you, Alexander, and we'll start the thing.
Thank you for the great introduction. So, yeah, again, don't hesitate to ask questions if you have any. Do you hear me well? Right? Just checking. Okay. Okay, so this is the third and the final session of the Data Structures Intro series. So today we are going to talk about graph traversal and pathfinding. So again, it's me and Andrew who hosted 2 previous events, and today again we are here. So again, we had the first session dedicated to generally algorithms and data structures overview, common sort and algorithms, and then this is the last one. So do not hesitate also to check out the 2 previous ones because they can be helpful to you on your journey of learning algorithms and data structures. So, yep. Okay, the agenda for today, like we had some brief intros. We are going to have an overview of the graph. Then we will see how we can store and create a graph. Maybe we'll even have a demo. It depends on our time availability. Then graph traversal. We will do depth first search and breadth first search, and we will definitely implement it. So it will be a live coding session. So if you want to follow along, you're welcome to do so. And the last point would be to like questions and answers. So yeah. Okay, let's start. So graphs. We actually covered graphs a little bit during our first session. As during the data structures intro. So, but this session is specifically dedicated to graphs. So again, we will look at different operations, analyze graphs, and again, we'll see how you can traverse them. So yeah, let's just jump into it. So, okay. Just as a reminder, like, if you attended our previous sessions, we talked about it already, but it just to refresh and to remind everyone. So graphs are essentially a set of nodes and connections. So, and there are 2 different types, like, yeah, not 2 different types, but weighted, unweighted graphs and directed, undirected. So important to remember that graphs are nonlinear data structures, while lists, stacks, and queues are linear. So what it means, essentially elements do not go one by one, like in a line, so not linear. So this is a graph, right? So we have 2 different, I would say, pointers. So we have like B connected to C and D connected to B. So it's nonlinear. Whereas, like, again, lists, stacks, and queues would be linear. So this is important to remember. Then also, one note, we will talk about graph data structure, not graphs that you maybe saw in math classes. So again, it's also important to understand. And yeah, so let's just remind what weighted, unweighted, and directed, undirected graphs are. So here we go. Let me take a pen. So weighted, unweighted, it actually means if edges, so if these connections have any weight on them, so they have value like 8, 9, 7, etc., it means a weighted graph. It is a weighted graph. If we have if we have specific directions, like in this graph, so you see arrows, it means it is directed graph. If we didn't have them, it would be an undirected graph. Okay, so pretty simple. Okay, let's just again refresh some terminology here. So vertex is essentially nodes in a graph. So A is a node, B is a node, C is a node, etc. And edges are essentially, sorry, A, B, C are vertices. So again, nodes in the graph. And then edges are these connections between the vertices. Okay. Okay, cool. So about graph applications, so we use them essentially everywhere. Social networking, pathfinding, recommendation systems, the graph databases, and many more. So let's just take as a simple example, so let's just, if I can zoom into it. So here we have a graph, right? So in social media, so imagine this is a social media like Facebook or I know Twitter or whatever social media you want. So this is probably the way how they store their data using graph. So for instance, this is one person. So imagine this is you, and you have a bunch of different friends. So this is how different connections are stored, right? So you have connection to this person has connection to that, to these people, etc., etc. So again, social networking, then pathfinding. So essentially, if you want to find the shortest path from point A to point B, like Google Maps, right, is a very good example of pathfinding, right? So they store different places as vertices in the graph and connected with different edges, right? Like roads or different ways, right? But obviously, Google has a better modified version, like an enhanced version of a graph. Yeah, then we have recommendation systems. So again, graphs are extensively used in AI, machine learning. So to analyze and store, again, different data. Then we have graph databases. To be honest, I learned about it. It's just Andrew who told me. So
yeah, it's basically like anywhere that you can think of things connecting to other things, like if it's cities or if it's like flights connecting some cities, or in graph databases, like some entities that are connected by their relationships. There's a lot of things that you can, like a lot of different applications where you can think of where graphs are used. The majority of the cases are something like real life pathfinding, right? Like map data structures, your streets, your intersections, things like that. But yeah, there's plenty of things, and we'll kind of, as we go during the session, we'll learn how we can kind of understand the properties of the system that we're working in, like different I don't know, shortest paths, or just analyzing all the data points in such data structure. It becomes really, really useful if you know where to apply it.
Okay, so this is like about graph applications. Then again, like a refresher, graph types. So this graph is unweighted and directed graph. I just want to refresh it to you because it's important for us to understand what these types are, because so you can distinguish them when we do our implementation. So graph types, again, this is unweighted and directed graph. So why it's unweighted? Because the edges, so the connections, do not have any weight to them. And also it is a directed graph because we have specific directions that are that we can move with in. So an example where this graph can be applied is like, think about Instagram. To be honest, I'm not I do not use Instagram, but it's just one of possible structures they use to store their connections. So imagine this is you, right? So, and you follow somebody else, right? So you have one direction, but this B does not follow you. So you don't have this two-way direction, right? So then we see that B is following C, but C is not following B, right? So this is like a possible way how Instagram could store the data, right? So using with following. so like A follows B, then B follows C, but C doesn't follow B. So in this way, I hope you got the point. Also, another possible use case of this graph would be, again, Google Maps, like one-way or two-way roads, right? So some roads you can move just in one direction. So imagine city A, right? Just a second, let me erase it. So you imagine you have city A and city B, or no, let's do like shop A and shop B, and there is a road, but this is just one-way traffic. There is just one-way traffic, so you can go only this direction, right? You cannot go back. So for instance, we have another two locations like D and C. So imagine we had like two ways, like both directions. So that would mean that we can move from B to C and C to D. So again, this would be a two-way road. So this is another way how you can represent this, like these roads and different directions, right? You can move in. Okay. Cool. Next type is unweighted and directed graph. So unweighted, why we don't have any weight on the edges, and undirected graph because we don't have any specific directions here. A possible use case would be probably Facebook. Again, I'm not sure what these social medias use, like what types of graphs they exactly use. It's just like my assumption that might help you to understand it, where it can be applied. So unweighted and undirected graph, a possible use case can be maybe Facebook. So if you follow if you add a friend, right? So you both become friends at the same time, right? So you don't have this thing like in Instagram, let's say, when you follow, but the other person does not follow you, right? But in Facebook, like you both are friends, so this direction actually kind of does not really make sense in here. So this could be another use case of this type. Okay, next type is weighted and directed graph. So let's say, so again, weighted why? Because the edges have weight, and directed because we have specific directions. Possible use case, again, probably, again, Google Maps. Because like, imagine this is a highway, or that's a weird highway that it can move where you can move just in one direction, but still. Okay, and imagine it's road segment, which is which has the length of 8, right, kilometers, let's say, and then from B to C you have another road segment which is 2 kilometers in length. So this is again how you would use this type of graph. And the last one is weighted and undirected. So we have weighted, so essentially we have specific values to the edges, so to the connections, and also we do not have any directions, right? So we can move in both ways. Okay, cool. Are there any questions so far? Just I'm not looking at the chat, so I'm just
no, everything is good. Yeah, if anybody has any questions about what we're covering, please feel free to drop them in the chat. Either I'm going to answer that, or we'll kind of discuss it amongst ourselves, figure things out. But yeah, we're good.
Cool. Then now we talked about graphs, right? So I hope you understood like the purpose of it, like how it looks like. Again, this is an abstract concept, so it's these visualizations are just helpful to you to understand what a graph is. So now we need to find out how we store the graph, right? So how will we do that? So how would we store this graph, for instance? So how would we create this graph, or how we would do this graph? Okay. So before actually we start, I just want to emphasize that during this session, we will implement this type of graph. So we will do unweighted and undirected graph, since it's like the simplest one, and we don't want to add extra complication to it, since it's like a good start for everyone. And later, like after the session, you might Google something or like check out the other types and how you can implement them. Okay, and so again, first important unweighted and directed graphs. This is what we are going to implement, and we are going to talk about two ways of implementing a graph. The first one is adjacency matrix, and the second one adjacency list. So let's just go into it. Okay, cool. So adjacency matrix. So this is the first way you could kind of create a graph. So essentially what a matrix is a two-dimensional structure, right? So like two-dimensional array or something like this. So it's essentially like a table, as you can see on the right. So this graph on the left, here, this one, is, again, unweighted, undirected. And this is how you would represent it using the adjacency matrix, okay? So now let's just learn how we can read this adjacency matrix. So rows, so these ones, rows represent source vertices and columns represent the destination vertices, okay? So this is where we go from, and this is where we go to, okay? So let's just read it row by row. So here we have A to A, like we cannot go from A to A because we are there. Then we see A to B. Yes, we have one. So it means, yes, we have a connection between A and B, okay? And then we say, do I have a connection between A and C? No. So 0 means no, 1 means yes, right? Alternatively, you could store like true or false, okay? So then A to D, do we have a connection A to D? No. Do we have a connection A to E? No. Do we have a connection A to F? No. So this is how you would read a row. Let's just, so yeah, alternatively B. So we can see here that B has connections to A, right? So to A. So we go from B to A, and we have connection here. And then we can see we have connection from B to C, right? And we can see that we have a connection from, where's my mouse? Okay, from B to D. Yeah, cool. Then the same thing with the C, D, E, F. So this is essentially how you would store, one way that you can store your graph, right? So again, let's just pick random. So here we see that F, for instance, has just one connection, and it is from F to E, right? And that is correct. Okay.
We have a quick question from the chat that I think is an interesting one. So Icarus is asking if we are covering multigraphs. I don't know, Alexander, do you know what a multigraph is, or of that type?
To be honest, I'm a little bit no.
If I'm not mistaken, Icarus, you can correct us if you're wrong, but I think multigraphs are either graphs that consist of different multiple components, so they can be like not two components of the graph could be not connected to each other, or either there might be edges that point from one vertex to its own, like there's like loops to edges pointing from one vertex to the starting vertex, basically. I don't really remember which one is which. To answer your question, we will just be covering like undirected, unweighted graphs, because those are the most simple the most simple representations of the graph, and all the algorithms are going to work on those types of graphs. But thank you for asking, because there is a lot of different types, not just the ones that we mentioned. Those are maybe the most popular ones. But for sure, maybe you can improve our algorithms to work on other types of graphs, and that's something we can explore later on. So yeah, thanks for the question.
Yeah, I'm probably like I understand what you talk about, but like I didn't know the specific term. So okay, thanks for that. Yeah, again, as Andre mentioned, we just covered like basic stuff so you can get started with the graphs. So yeah, in this case, we will implement like something like this. So, and weighted and directed graph. Okay. And then I want to switch for a second here. And yeah, do you hear me? Hello?
Yep, you're good.
Okay, cool. Yeah, just confirmation because I switched the screen, so I want to ensure that I'm still there. Okay, so I just opened a Wikipedia page, and it has like 3 different representations. So again, you can just read about them. So we covered just in this session, we'll cover just adjacency list and adjacency matrix. Yeah, but you can read about like graphs maybe more in detail using this article. So just type graph abstract data type, and there you'll be able to find like different information that you might want to learn. Okay, but yeah, we will stick to that for now. Yeah. Okay, now since this was the first way that we could store, so again, I hope it's not complicated. So again, rows represent the source vertices, and columns represent the destination vertices. This is about adjacency matrix. And then adjacency list, we have another way of storing graphs, which is adjacency list. And this is essentially how you might represent it. So you would have a list of all the vertices in the graph. So in this case, you see that we have A, B, C, D, E, F. So 1, 2, 3, 4, 5, 6, and we have 6 vertices in the graph, right? And then we store just corresponding connections. So how we read it? Let's just learn how to read it. Essentially, we have a vertex A, and we say it has connection to B, which is correct, right? Then we have B, which has connection to A, to C, and to D. So cool. Then C, we have connection to B and to E. Then D, we have connection to B and to E. E, we have connection to C, D, and F. And F has connection to E. So again, I hope it's straightforward, not very complicated. This one is actually the type we will implement. We will discuss the trade-offs of each one on the next slide. Yeah, but just generally, like we will use JavaScript for the demos and for the code, and you will see GitHub code. Code on the GitHub also is written in JavaScript. So yeah, we kind of assume that you have basic knowledge of JavaScript. Yeah, and in different languages like I know C#, Java, etc., you might use like dictionaries, maps, right? So different languages have different terms to the same thing, essentially. So yeah, so that's it about adjacency list. Now let's just compare why you would use one over the other, right? So what is the adjacency matrix good at and what it is bad at, and the same thing with the adjacency list. So just yeah, like to be honest, I also just when I did my research, I found out what this modulus mean. So actually, we is let's just imagine we have different. Yeah, let me start all over again. So in the first session, we had the discussion about big O. So right, and we talked about it, and we understood that Big O helps us to compare different approaches to the same concept or solution, to the same essentially goal, right? So we just compare and see the trade-offs of one solution over the other. So, and in this case, so this is the table which has big O's of adjacency matrix and adjacency list, okay? So we say that V is a set of vertices. So, and modulus V is the number of elements in set V. So essentially what it means, the number of vertices in the graph, okay? So how many vertices the graph has. So in this case, we have 6. So then modulus V would be 6, right? Then we have edges. So with E is a set of edges, modulus E is the number of elements in set E. So essentially what it means the number of edges in the graph, right? So in this case, it would be, let's count it. So 1, where is it? So 1, 2, 3, 4, 5, right? Okay. And this is like what our calculations are based on. So, okay. So now let's talk about this table that we see. I hope these symbols are clear, like what modulus V and modulus E are. So yeah, about adjacency matrix, let's talk about it. So when we want to add a vertex, it's actually all of V squared, right? So this is the number of vertices squared, roughly. Again, this is a simplified version of Big O, so the actual values like might differ. But again, since we simplify Big O because we care about big picture, so this is it. So here, if we go back to the slide, we have essentially a table, and if you want to add a vertex, your time will be of V squared. Why? Because essentially we need to we have like the number of rows is the same as the number of vertices, and then the number of columns is the same as number of vertices. So you just multiply them, and you need to iterate all over them again to add just one vertex. Okay, so this is like bad time complexity, right? If you want to add a vertex, whereas the adjacency list is of 1, because essentially you just add a new key value. So it would be like, I don't know, let's say you want to add a node called K. So you just want to add a K, and that's it. So this is just of 1. So it's a constant time to create a vertex. Then about adding an edge. So adding an edge is very simple in both of the graph representations. And here we see that it just, you need to say, oh, if you go from E to A, right? So you might want to create a connection between them. So if you want to create a connection, you just change the value from 0 to 1. And then here you would also change this one. So A to E, like both directions, right? So this is why it is constant, essentially. Then we have in adjacency list, again, it's also simple because you just, if you want to, let's say, add connection from, let me erase it just a second. So if you want to add connection from F to A, let's say, so again, we will talk about it more in detail on the next slides, but it just, since we have this table here, so I just explained why we have this specific time complexity for each one. So, okay. So what would we do here? Why is it constant time? Because we would just add, so F to A, so we would just add A here, right? And then A to F, so we also would add F here, right? So again, and this is also constant time essentially. Then remove vertex, again, squared, number of vertices squared. And then here to remove a vertex, we need it is essentially number of vertices plus number of edges. So all of number of vertices plus number of edges. So in adjacency list. So again, you can just see this table, and I hope you got the main point, like how you measure this these time complexities in these graph representations. So I hope it's not very complicated. And then the only thing I want to talk about as well is here storage size. So again, it is essentially what is like, this is a space complexity essentially. This storage size is a space complexity of different again graph representations. Why is it of v squared in an adjacency matrix? Because as we can see, this is a number of rows, it's the same as number of columns, and each of them are essentially number of vertices. So okay, so we have, if we have 6 vertices, then we have 6 rows and 6 columns, and thus we need 36, right? 6 by 6 different spots to store these connections, right? If we had like 100 by 100, that would be how many? 10,000, right? So 10,000 different again spots to store these connections. And it's very inefficient on sparse graphs, right? So if you have like million different nodes, it's very inefficient to use adjacency matrix. And again, about adjacency list, it's just the number of edges and the number of vertices summed up. Okay, so all E plus E, and this is essentially the space complexity of this solution. Okay.
One quick suggestion, actually, that we had in the chat. Udit is asking like to explain what is incidence in the path matrix. So I'm not too sure what a path matrix is, but the incidence matrix is definitely another representation of a graph. Today we'll only be focusing on the adjacency matrix and the adjacency list, because I think the most popular one is the adjacency list. Sometimes you would leverage different storage options depending on what is your use case, right? Like maybe you want to use like an incidence or an adjacency matrix, but the adjacency list will be the most popular one, and that's the one we will be using in our implementations as well. But yeah, thank you for pointing this out. There is more ways to store a graph than we're just showing. And if you want to explore them more, please drop by the Discord server. We'll chat about it. We'll kind of explain what those are if you're interested, and what are the drawbacks, or any like why one is better than the other. Yeah, thanks a lot for pointing that out.
Yeah, good point. So again, these are just two, let's say, common ways. Adjacency list, sorry, adjacency list is obviously more common. So I just want to make a small conclusion about these different types. So again, adjacency list. So based on this row, or based on this table that we have, we can conclude that it takes up less space, right? So storage size is less in adjacency list than in adjacency matrix for sparse graphs. So if you have, again, 1 billion items, like obviously you probably would go with the adjacency list, because it would be very inefficient to use adjacency matrix for that case. Then adjacency lists are faster to iterate over all edges, and they can be slower to look up a specific edge, right? Adjacency matrix, they take up more space, as we see here, and they're slower to iterate over all the connections. So if you want to build a graph based on this adjacency list or adjacency matrix, it would be quicker to use adjacency list to build a graph rather than this one. Okay, and also adjacency matrix is faster to look up a specific edge. So if you want to look up a specific connection between, let's say, A and C, obviously it's very easy. So you just say, is there any connection between A and C? And that's it. Okay. So based on the reasons I just said, we will use adjacency list because like in real world, we have huge data sets, right? Again, social media, obviously they can have billions of data points of different uses, and it's more efficient if you use adjacency list. And again, in this session, we will just talk about undirected and unweighted graphs because they're simple to implement as a start, and again, just to get you started. So, okay, cool. Let's move ahead. So here we have different operations. So again, we talked about different ways you can store it. Again, these are just two. Obviously, you can have more. We talked just about this one. So how do we implement this one, like in real code? How do we create this graph, right? So we will have 4 basic operations: add a vertex, add an edge, and then remove an edge and remove a vertex. Okay, so add, remove vertex, add, remove edge. Okay, so the first operation I want to talk about is add a vertex. So essentially, when you have this this will be an instance method. So you have a graph object, and then you say add vertex Toronto. Okay, and when you do this, what should happen to sorry, to the graph is that it should have in its adjacency list Toronto and an empty array. So let's just give me a second. I will just open this one. So this is how our graph actually looks like. So yeah, if you want to follow along, or for the DFS and BFS, again, I will just show you the code. Due to time limitation, I cannot like implement it with you. Sorry. These simple operations. So here we have add vertex, add edge, remove vertex. So this is essentially how we represent a graph. We have a class called graph, and we have constructor, and it just has, so a graph has just one property, which is adjacency list, okay? And then based on this adjacency list, like we manipulate this adjacency list, okay? So this one, this adjacency list here, okay? And we just add different key value pairs in order to store our graph. So here I have add vertex, and let's just again go over the pseudocode. Now you understand how to, like, how this graph is created, right? So we just class graph, and then you have constructor with one property called adjacency list, which is essentially like a dictionary, a map, whatever, and where you store key value pairs, okay? As we discussed earlier in adjacency list. So if you don't know what I'm using right now, it's actually it's Google Developer Tools snippets. So if you want to access the same thing, you just right click on any page on your Chrome browser, and then click inspect, and then you click on sources. And then here, if you don't see snippets here, you will just click on this one, and you should see snippets here. And then you will just be able to write your like different files. So file 1, and there you would have like something like you could say class, again, graph, and then you have just constructor with this dot adjacency list, which is just a dictionary, okay? So this is how you can essentially write your code if you have any preferable IDE, like if you like Visual Studio Code or any other IDE, you're welcome to use it for the demo portion. So if you like, these snippets are just universal, so it just anyone can open it because I hope everyone has a browser on their computer installed. So okay, this is how the graph is structured. So now again, let's go back to this add in a vertex. So let's just read up pseudocode. So add a key. So what we need to add a vertex, we just need to add a key. Just a second, I want to erase it, not to confuse you. Okay, cool. Add a key to the adjacency list with the name of the vertex. So we here have graph.addVertex, Toronto. So what we do, the first step, add a key to the adjacency list with the same name of the vertex. So we pass Toronto and we create a key called Toronto in our adjacency list, okay? And then we set its value to an empty array. So here we set its value of this key to an empty array. So what this essentially means, we just created a vertex called Toronto, okay? Okay, and that's essentially it. So it's as simple as this. So if you want to exit this code, again, it will be just for these simple operations, we will just go over the code, but for DFS and BFS, so depth first search and breadth first search, we'll just, we will write some code. So what did I want to tell? Okay, GitHub. So if you want, you can actually use, just a second, let me switch back. So yeah, you can just go over to the GitHub. I don't know if Andrew, okay, cool. Andrew already put it
there. I'm
so,
one, and I'm also going to paste it in the chat. So if you have any kind of questions over the code or want to go over it again, feel free to use our GitHub repo.
Yeah, so let me just want to open it. So we have this code, all the code that we will write today is already there. So you can just maybe go ahead and take a look at it, like these basic operations. So again, this what you will see there. So this one, we have a graph, a class, and we have a constructor, and we have an instance method called addVertex. So we have vertex. We pass a vertex, right? So like here. So we add vertex and we pass a vertex name, which in this case will be Toronto. So we say if vertex is not in the adjacency list yet, then we create it. So again, we just follow the strategy that I described here. So we add a key to the adjacency list with the name of the vertex and set its value to an empty array. So we add a key to the adjacency list, okay, as this vertex, and then we assign its value of this at this key to an empty array, okay. So what this will do, it will not overwrite if a duplicate. So like some protection is preferable, right? So if you have like the same exact node, you don't want to overwrite it because maybe you have some data out there. So you don't, to avoid data loss, you would just have this condition to check if a vertex is not in the adjacency list yet, then you create it, okay? So this is how you would add a vertex. So again, vertex is just a node, okay? The data point. So, and just as a disclaimer, we do not have any error handling or special like, let's say, yeah, again, no error handling. So some errors may occur. So it will be your job to add some error handling in these functions later. Again, don't worry, we will just go over them in a second. So yeah, but here we just focus on the basic concept, like the core, so you understand how it works. Okay, so we do not focus how to handle each specific error. So yeah, that's just one point I want to mention. So, okay, after, actually, let's just see how it works, okay? So before I do this, so I just will comment it out. So I have some code here. So I create a graph, okay, which is new graph. And then I say graph at vertex Toronto, New York, and Calgary. So if I click execute, and then I type graph, now you will see that I have a graph here. Let me just do this. And we have an adjacency list here. And if I click here, so you see here, we have Calgary key, and it has an empty array as its value, then New York and Toronto. So this is our adjacency list, right? So step number one, we created a graph. So not a graph, vertices. Now, step two would be to add edges, right? To add different connections, because like it doesn't make much sense if we don't have any edges, right? So this is how you would add an edge. Again, it's very simple, very straightforward. So add in an edge, find vertex 1 and push vertex 2 into the array. So, and then, so imagine we have add edge. So the first, and what it says essentially, again, we implement undirected and weighted graphs. This is very important to understand here. If you want to implement a different type of graph, you would use something like a different logic, right? So here we have, so we want to add an edge from Toronto. So imagine this is our graph so far. So we have 3 vertices. So we have Toronto, Calgary, and New York. We don't have any edges yet, right? And I want to add edge from Toronto to New York. So, and vice versa, okay? Because it's undirected. So to do that, I need to look at the instructions, find vertex 1 in the adjacency list and push vertex 2 into the array. So what it means, so we find the vertex called Toronto, and we push vertex 2, which is New York, into its array. Okay, so like this, Toronto, New York. So what it actually says, we create this connection, so from Toronto to New York, but then we also want, like vice versa, since it's undirected graph, so we want both ways. So we say New York to Toronto as well. So we have just, and we create this one as well. So it will be, this would be the result. So again, find vertex 1 and push in the adjacency list and push vertex 2 into the array. So like here, and then find vertex 2, which is New York, and in the adjacency list and push vertex 1 into the array. So I found New York and I pushed Toronto there. Okay. So if I go here and I just take a look at this one. So add edge, you see the function. So we have add edge, again, no error handling, just you might want to check if both vertices exist. But again, this is just the core, the most the foundation, the fundamentals. So we do not have any error handling here, but you might want to add it. So yeah, this will be like your task to enhance the code as much as you can. Okay, so
sorry to interrupt you. We had an interesting question coming in. So Prajwal is asking if like the vertices are being added like in a stack fashion with the first in, last out. I guess I'll let you answer this one. For these operations, what are we using as our data structure?
Are vertices getting added in stack fashion? To be honest, like if you add a vertex, you mean here, right? So yeah. In the, okay, I got the question wrong. Where is it? So in here, right? So if I add another connection from like Toronto to Calgary, let's say, then I would have Calgary here. right? So Calgary here, sorry for I cannot write here. Okay, Calgary, and then we would have here Toronto, okay, T. So yeah, if you meant by this as a stack fashion, then oh, sorry, then yes, that's correct. So yeah, so you add the edges in this stack fashion essentially. So last in first out, so one by one. But actually, it really does not matter since, like, again, yeah, this is preferable. So this is how we do that. So yeah, the answer to your question is yes. Andrew, do you have anything to add?
Yeah. I mean, like it doesn't really matter. Like in JavaScript, your lists, they have this push function, which might you might think of them as tags. They are actually not. Like you're just adding an element to the end of the array. It doesn't matter if you use a stack or a set or a list. We're just storing a set of values for each vertex, like adjacent, their neighbors for each vertex, right? Like it doesn't really matter what we use. Yeah, thanks for the question.
Okay, yeah. Okay, now we talk about, okay, let's go back to here. So again, yeah, just follow this plan that we put there. So find vertex 1 and push vertex 2 into the array. So this is what we do essentially. So this is that adjacency list at vertex 1, we push vertex 2, right? And then at adjacency list vertex, adjacency list we're at vertex 2, we just push vertex 1. So I will uncomment this code. Okay, so like this, and then clean it for a second. And here, you see, we executed all of that code now. So we should have vertices and edges as well. So if I type graph, so we see here in our adjacency list, we now have these connections. So what it means, we have connection from Calgary to Toronto and from Toronto to Calgary as well. Then we have New York to Toronto and Toronto to New York as well. Okay, so this is essentially it. Basic 2 operations that create a graph for you. And that's essentially it, like how you create it. Now let's just briefly talk about the removing edges and vertices. Okay.
I think we can skip like covering the codes exactly. If you want to look into how that all works, feel free to check out the GitHub repo. Just for the sake of time, I think we can skip over these operations since those won't be used for our like main main topic, the DFS and the BFS.
So the first two, yes, add vertex, and edge are important for our DFS and BFS. But these ones, again, we have pseudocode here. You will be able to check our Git repo, and then just follow this pseudocode, like just 2 lines, and try to figure out what it does. So find vertex 1 and remove vertex 2 from the array. So here, if I want to remove Toronto, and if I want to remove edge Toronto, New York. So imagine we have like this graph now. Just a second, right? And we want to remove this edge, right? So this is how would you do that. And so find vertex 1 and remove vertex 2 from the array and vice versa, right? So, and this is what you end up with. Again, check the code on the GitHub, and it's not complicated, just again, a couple of lines. So yeah. Now about removing a vertex, again, very briefly, remove all the edges connections from the specified vertex first, right? So if we just remove the vertex itself, like the key, then we still would have the edges, right? But if we remove a vertex, we need to remove all the connections to it, right? First, and then, and only then, we delete this vertex by itself. So again, the first step, remove all the edges connections from the specified vertex. So we remove New York to Toronto, and we remove Calgary to Toronto first, and then we delete the key for the vertex. So we delete this key. Okay. So just again, 2 simple steps, and again, remove vertex. So this is what you would end up with. Okay. So again, check the code. We just need to keep going because we still have a lot of cover, and we have just 30 minutes left. Again, now let's start a graph traversal. Andrew, maybe can you ask like a couple of maybe answer a couple of questions and just mention something about it? I will just grab some water because my throat is a little bit crazy. Okay, just a second.
Yeah, sure. Yeah, while Alexander is doing that, so yeah, like graph traversal will kind of cover DFS and BFS. This session we won't go into more complex algorithms like Dijkstra's algorithm that is probably, or A star, like the popular ones, because it would just take like an hour to explain those in more detail and show how they work. I will actually like briefly talk about the structure. Oh, okay, Alexander is back. I'll not talk about it then. Well, yeah. So just the graph traversal idea is to basically go through all the nodes of the graph and kind of look into them and see what updates, what properties we can see in them. We'll be covering only the DFS and the BFS. Those are like the basic algorithms that you should know on graph traversal. So yeah, let's go into it.
Thank you for a short break. I'm sorry. So hopefully now I sound a little bit better. So we have graph traversal. Let's just we will talk specifically about like 2 major algorithms, which are depth first search (DFS) and breadth first search (BFS). So the point of these algorithms is to is to visit every vertex in a graph. So this is essentially what these algorithms do. They try to they should visit every single node in a specific graph. Okay. So here, and it is the base. So both of these algorithms, DFS and BFS, are the base for pathfinding algorithms and other Henry, did you mention any implementations, like other implementations? No, not implementations, but applications of DFS and BFS?
No, I haven't mentioned them yet, but yeah, let's kind of go over why they might be used.
So yeah, like pathfinding, again, very common. Then we have other algorithms like how's it called? Topological sort, right?
Yeah, topological sorting. So basically the idea is that so we learned like what graphs represent and how to store them. Now we kind of want to learn some properties on graphs. Maybe you want to find out what is the shortest path between 2 vertices, or like you want to traverse the graph and analyze all the vertices in some particular order, sort the vertices based on their directional connections. That's called topological sorting. All of those different things, finding cycles in graphs is a very meaningful one, might be very, very useful in your use case, right? It really depends on what you're looking for and what the problem is that you're solving is. But yeah, just the idea is that DFS and BFS are the starting points for a lot of other algorithms, and they can be used to find out different properties about the graph.
Yeah, cool. Thank you for that note. So yeah, essentially, so DFS, let's just dive into it. So DFS, again, 2 common, like Henry just mentioned, uses of DFS. Again, identify the properties of the graph. So you just want to understand if there are any loops in the graph, like you see here, the DFE. So this is called the loop, right? And then maybe how nodes are connected between each other. So again, to identify different properties of a graph, you would use a DFS, so depth first search, and then again topological sort. But anyways, let's just understand how it works. So again, the point is to traverse, so to visit every single node in a graph, so every single vertex in a graph. So imagine, so depth for search is go deep into the graph. So if we have like this graph and we start from A, okay, so we need a starting point. So we say it's A, okay, then we need to we look at the neighbors of A. So we see what neighbors of A there are. So B and E, and we will go in alphabetical order. So B is earlier than E, so we will choose B just for consistency. So B, okay. So we go B, and then we visit neighbors of B. So a neighbor of B, so C or D. C is earlier than B in the alphabet. So again, for consistency, we use we go C. So C like this, and then since C does not have any neighbors, we'll go back one step, and then we go to another neighbor of D of B here, which is D. So this one, and we track it D. Okay, and then we have D. So D has three neighbors actually, but two neighbors that have not been visited yet. So E and F. We will go to E because it's earlier in the alphabetical order. Again, alphabetical. It doesn't matter which order in the alphabet. Like it just I use it for consistency. So you can go either to F or E, but I go to E because again, just for consistency. So I follow the alphabet. So here we go to E, and then we say E, does it have any neighbors not visited? Yes. We have F. So this is, and we go here. So this is depth first search. So this is the sequence, how you would traverse this graph, okay? So you would go from A to B to C, then you would go to D, okay? So again, A to B to C, then back to B, then to D, to E to F. So this is like depth first search. So traverse the graph, visit every single vertex, okay? So this is the first approach. So this was just a draw how you might use it and how it works. And now let's just take a look at our adjacency list. And so before we implement it, we just need to understand how our adjacency list is manipulated, okay? How it's exploited, not manipulated, but exploited is the better word. So let's start. So again, we start with an A. So imagine this is our results array. Okay, so this is where we will store the sequence of the vertices we go through. Okay, so A is the first one, so we push A into this results, and then we say that A is already visited. So I mark it. A is visited, right? So we don't go back there unless it's okay. So we just say it's visited. So we will not add it the second time to the results. Okay. The second, now we check the neighbors. Okay. Now look at this one. So we have A. We start with an A. Okay. And we have two neighbors, B and E. So we will pick the first neighbor, which is here, B. Okay, so I go to B. So I add B to our results array, and I mark it as visited. Okay, then I have B. Again, these, like you see the lines, red lines, I added them, so it means they're already visited. So B, we visited B, A already, so you just are not confused about it, okay? So we don't not remove these connections from the adjacency list. I just just for visualization for you to understand. It just means they're already visited. So you're just not to confuse you. Again, this just means this specific vertex has already been visited. Okay. So, okay, B. Now we take a look at the B. And B has 2 unvisited neighbors still has 2 unvisited neighbors. So C and D. We pick the first one, C, okay? So we push C into our results list and we mark C as visited, okay? Cool. Then C, we check C and we see, and now we discover that C does not have any unvisited neighbors left. Okay, so because B has already been visited, so we don't have anywhere to go. So that means that we just will go one step back. So we go to B back. Okay, and now check again. Does B have any unvisited neighbors? Yes, it still has one unvisited neighbor, which is D. So I say I add then D to our results and I mark it as visited, okay? So then we have, what else? Now we have D and we check, does D have any unvisited neighbors? Yes, it has E and F, so we pick the first one, which is E. So E, we add it to our results and we mark it as visited. And we check, does E have any unvisited neighbors left? Yes, it has one neighbor that is still unvisited, F. So I add F to the results and I mark it as visited. And now I check F and F is already done. And we see that here, essentially we traversed everything, right? We visited every single node. So that means we are done. Okay. So I hope it's kind of, again, I just make this visualization to help you understand, again, step by step how it works. Now,
sorry, just a very quick question before we move on to what you explained and how DFS works. Raf is asking if we would also backtrack and check D to F when we kind of, even though we finished on F, we finished analyzing the graph, do we still backtrack and check D to F, for example? And I think like by backtracking, you mean for D, you want to check all of its neighbors. When we only visit D, when we come to D, E and F would not be visited, right? So they both would be valid options to go into. But after we analyze E, F becomes visited. So even though it is visited, we don't go in there, we still want to check D to F, see that it's visited. We won't be analyzing it again. But yeah. We're going to kind of look into different implementations of DFS, and it's going to be more obvious what backtracking is. And especially if we're using like a recursive implementation, which Alexander will talk more about. Well, I hope that makes sense, and we'll kind of go into implementation now.
Yeah. So actually, to answer your question, yes. So would you have to backtrack and check D and F in the algorithm? Yes, it will go back and check again, and it will understand no, or we already visited it. So yeah, do not put anything in the results array. So that's essentially it. So again, we will have 2 implementations of DFS. We will have one iterative, recursive, the first one, recursion, using recursion, and the second one, iterative, so using a loop, okay? So now just to take a look at the pseudocode before we implement it. So we have a function called DFS, which accepts a start vertex. Okay, so we add, so the first step would be to add the start vertex into, stop. So, sorry. we create a DFS function which accepts the start point. So in this case, it would be A, and then we add and then we will have recursive algorithm to add vertex to the results array. So like this results array that I just showed you. So, oh, what happened? Okay. Okay. So we would have this array. So we also what we would need to do before actually this algorithm, we would need to create results array. We would need to create also a I don't know, a special tracking system, like not system, but we'll create a dictionary. So which we would call visited. So this is where we would store if a vertex has already been visited or no. So we would say A was visited, so true, and then B was visited, etc., etc. So as we go, we will have this visited dictionary that essentially will store the if a vertex has already been visited or no. So yeah, and then we have this these steps. So add vertex to results array, mark vertex as visited, okay, and then for each adjacent vertex, if it is not visited, we recursively call DFS on it. So if it's a little bit confusing, don't worry. We'll just go over the code right now. We actually will write it. I do want to write at least DFS recursive. To be honest, I like the way this recursive solution works. So I hope it will not be complicated for you. So just a second. Okay, so I will again use snippets. Where is it? Where is it? Where is it? So I will have, just let me open it for a second. Okay.
12 seconds later.
Yeah, good. Then we have graph, and then let me just copy some code over here. So we will just copy this. Again, you can just go over to the GitHub and copy some code. We actually do not need these for this particular DFS implementation. We just need add vertex and add edge. So yeah, these are the most important here. So
sorry, Alexander, could you make the font just a bit bigger, if you can? Perfect, thank you.
Okay, cool. Wonderful. So, and now let's just implement this DFS recursive. So we will call this function, again, it will be an instance method, recursive. And then it accepts start, okay? I'm calling it DFS recursive because we will have DFS iterative, okay? So with a loop, this one uses recursion. So before actually we do anything, we need to create let results, as I said to you. So we need to create results array, which will store the sequence we visit the vertices in. So, and then we have visited hatch map or dictionary, whatever you'd like to call it. So visited dictionary, which will store essentially if specific vertex has been visited already or no. And then we have an inner function, which I will call DFS, which will be a recursive one, okay? So this is an outer function, and this one will be an inner function. Why? Because if I call this one recursively, these ones would be reinitialized and redeclared again, and we don't want this. We want to give them like to accumulate data, not to like refresh them all the time. So again, we just need a helper function inside. So in this case, it would be DFS. So when I accept a vertex, and here we just follow the approach I just mentioned there. So add vertex to results array, mark vertex as visited, for each adjacent vertex, if it is not visited, recursively call DFS on it. So let's just start with 2 first steps: add vertex to results array and mark vertex as visited. So we say DFS what? Add vertex to the results array. So this one. Okay, so results that push. Okay, to add to the array, we use a push function. So vertex. And then visited at vertex is true. Okay, so again, 2 first steps. Add vertex to the results array, mark vertex as visited. So this is what we essentially do, right? And then the next steps are for each adjacent vertex, if it is not visited, recursively call DFS on it. Okay, so how do we check adjacent vertices, neighbors of this vertex? We have this adjacency list, right? So we say for let v of adjacency list, adjacency list at vertex, and then I say if vertex, if this neighbor, so what this loop does, it iterates over the neighbors of this particular vertex. Okay, so if we go back to the slides and we remind ourselves how the structure looks like. So this one, for instance, you see here, we have neighbors stored in here. So what this loop does, it just iterates over the neighbors for a specific vertex. Okay, so in this case, if we have like A, then it would iterate over this array, right? And if we have like B, it would iterate over this array. And what we do there, we check if the vertex has not been visited, if this neighbor has not been visited yet, we call DFS on this neighbor. Okay. So again, if we go back to our pseudocode, let's just read it again. For each adjacent vertex, if it is not visited, recursively call DFS on it. So again, for each adjacent vertex, this is a syntax. If you don't know this, for off loop in JavaScript, that means for each essentially. So for each neighbor of adjacency list, if it's not visited yet, we recursively call a DFS on it. And then the next steps would be just to call DFS, like this internal function. We need to call it with a start, right? And then we just return our results. Cool. So we save it. And then I just will show you. There is actually one problem that I will want to show you. So if I call, no, just a second. I need to create a graph first. So this is, again, go to the GitHub, and there you will see this code for a graph. So this is just to create a graph. This graph will look like this one. Okay, so to create this graph, we need to have this code. Okay, so this will add vertices, 6 vertices, and I'll add all of these connections. Okay, and now I call graph. So we just call it, and we see that we have our graph created here. So essentially, if you compare it to this one, you see we have A, B, E, right? Then we have B, A, C, D. Then C is B. Then D is B, E, F. And then E is A, D, F, and F is D, E. Okay, cool. So we have our graph created. Now, there is one problem that I will show you. I call DFS recursive with an A. If you see, there is a hint to us that it says type error is not a okay, no, I just need to, is not a function. Okay, no, just a second, I need to refresh it. So call graph, and then DFS recursive.
The name of the function might be different
Hey.
from what you have in the. You have.
Actually, okay, so there is a problem, and this problem is like that. Okay, I believe the problem is because I have another file with the same function, and maybe it just thinks that since I have it there, so maybe it is.
You're also missing an R. I think you have recursive instead of recursive. Like, just double check the name of the function you're calling.
Okay, cool. Thanks. So recursive. Okay, cool. Now I have the errors that I wanted to have. Okay, thank you. So I have error, and the error is like I did it on purpose. It's because I want to show that to you. We have uncaught, cannot read properly adjacency list of undefined. You see here, it actually cannot read adjacency list. Why? Because we have inner function, and if you know JavaScript or you've been working with it for like, I don't know, for some time, you probably know that each function defines the scope of this keyword. And this is the problem with the JavaScript in this case, that we cannot use this approach here. So what we do, again, this function redefines this keyword. So in this function, this keyword means a graph. But in this function, DFS, it means something else. So it gets redefined. And that's the problem what we have here, okay? So cannot read property, And what we need to do to solve this issue, we actually need to create what? Just a second. We need to create adjacency list, just a variable called adjacency list, which will store this .adjacency list. And now, when I call this now I just call adjacency list at this specific vertex. It refers to this .adjacency list. But again, we define this variable outside of this function, so this keyword does not get redefined. Okay, I hope it makes sense. If you are a little bit confused, just you can read about the scope of this keyword and just generally this keyword in JavaScript and how it gets defined. So yeah, it's just important. This is an important step to do. So now if I click it here and I do iterative, DFS recursive, and now I get that, okay, A, B, C, D, E, F. Cool. So, and that's what we get here. So if I take a look here, we have A, B, C, D, E, F, okay, and that's what we should get, and we get it. Okay, cool. Isn't it? So here, if I just call it like this, we actually can analyze it a little bit. And then since we have like, to be honest, like we planned 1.5 hours initially, we maybe will expand this session for a little bit longer. So I just want to show you, like, debug it with you, so you see the step, the execution steps, right? And there was a question about if we use the stack approach or how's it, fashion. Yeah, somebody said. So yes, you maybe will understand it by debugging this specific solution. So I call this function DFS recursive with start A, you see here. And now I create the results visited adjacency list. I define this function DFS, and then I call the function DFS at start. And now we see, and now let's see what happens. So we say results, which is vertex, current vertex is A, and we push it into our results. So we have results A, okay? So if I take a look, somewhere here, watch. No watch. Anyways, so we have results here as A, and then I go visit it, and now we have visited at A is true. So what it means is we visited A already, okay? And then in this adjacency list, we go over each neighbor of A, so B and E in this case, and we recurse, and if they have not been visited yet, we recursively call DFS on these neighbors, okay? So in this case, again, adjacency list at A, B, E, neither of them have been visited yet, so we just, we will call DFS on both of them recursively, okay? So I call DFS, and then another one. Actually, I should have probably step into it, but yeah, actually, I had to go inside, but I just skipped it. So maybe I should call it again. Just a second. So that's not very good. Just a second. Okay. Let's again. So visit it. Now go inside, and again, I do the same steps, but I just now I call recursively DFS a step into. So I just clicked the wrong button. So, and then you see here, now I have vertex B. So I do the same stuff with vertex B. So now results, we push vertex. So now we have results AB, and we mark B as visited. So here, and then we go over this adjacency list for B and curl recursively on each neighbor if this neighbor has not been visited yet. So in this case, it's C and D, okay, because A is already visited, as we can see here. So we say vertex is now A, you see here, and we check if it's visited. Yes, it's visited, so we ignore it. And now we check what is the neighbor now? C. So C, it has not been visited yet. So I go inside, and now I do the same stuff with C. So visited is true, and then I do this, and then C didn't have any neighbors, unvisited neighbors, like we can see, because B is already visited. So we go back. You see here, so somebody asked about like again the stack fashion. So we go back, and then we do this. We continue this loop with for B neighbors, and then now we do the same stuff with D. So again, you just go where it go, etc., etc. So after you finish it, you get this result. Okay. So yeah, I just didn't go over the whole graph because just a second. Yeah, because we, again, due to time, I would have done it if we had some time, like more time, but I just want to cover a little bit more concepts. So like some more concepts like BFS. So yeah, what you can do, it can be like your home task. You can just, again, debug it with these tools. So again, do not confuse this one and this one. So step into and step over. Yeah, and you can just debug it and see how it works internally, where you can just, again, pen and paper and to write everything. So, and I hope you will be good. So again, you just need to understand the basics of it. And so this is iterative. So I will not, I will just show you code for it, because
for the sake of time, I think we can just cover, just talk a little bit about the iterative approach, which will be very similar to the BFS implementation, actually. And then we'll probably cover BFS and wrap things up. We also have some questions that I would like to go over at the end.
Yeah, sure. So again, we have all the code for you on GitHub. We have the pseudocode, so you just read this, then you try little line by line, you go over it, and this one is exactly matches what the code has. So it will not be hard for you, I believe. Yeah, we did the best to try to explain it to you, so you can even study by yourself. So again, in iterative, we, instead of using recursion, we use a stack data structure. So again, referring back to our first session, we talked about stacks queues. So DFS, iterative approach, uses a stack, exploits stack. So what, and then you just, again, use stack, push start into stack, create visited list and results array. Let me just open it for you, and I'll just show you that. So create stack. So here we create a stack. Again, we simulate a stack using an array, but you can create your own stack data structure instead. Okay. So then we create visited, dictionary, hash map, whatever, to track the visited vertices, and then we create the results array to store the visited, the sequence of visited vertices, right? And then here we go. So create a stack, push start into a stack, create visited list, last result array. So I already pushed start into a stack by default there. Okay, since we use arrays to simulate this behavior of a stack. And yeah, so visited and results are here. So I just say that start is already visited, and then I just have a while loop. While stack length is not 0, I just pop the top element. Oh, again, referring back to that question about stack fashion. Yes, it is a stack fashion because we actually use a stack. And in here, in recursive, we also use a stack, but it's maybe you just don't not realize it. We use a call stack, essentially, to simulate this behavior, okay, that we can achieve by using a stack data structure. So you can either do recursive solution, which will exploit call stack, or you can use iterative, which will use a real stack, okay? I mean, the one that you create, I mean. Okay, so, and then you have a loop while stack length is more than, so while stack is not empty, then you just say vertex, we pop the topmost element, again, LIFO principle, last in, first out, right, stack, and then results.push, and then we iterate all over the, oh my god, the neighbors of a specific vertex, right, of that was passed here, and that was popped from the stack. We iterate all over its neighbors, and then if they are not visited yet, we push them into the stack and say they are visited. So again, I know that probably my walkthrough right now is not very sufficient for you to understand, because again, sorry, but time limitation, and especially you have some questions. Just again, we have pseudocode for you, we have code for you. Debug it, try to again, step by step. So pseudocode is very descriptive, so I hope it will make sense for you. So you should be good with this. And if I call, let's just before I do that, let me do that part. So if I call graph, ouch. If I call graph, ouch, sorry. I okay. It's not a function. Recur. Did I misspell it again? Yes, recursive. Okay. And now we have this. This is a recursive way. And this one, iterative, is a little bit different. So if I do iterative, it's a little bit different sequence. You see here, it's still depth first search, but it's a little bit different sequence. So we have here this way, and let me just go to the graph, to this one. Where is it? So this one. So how this works. Let me. Okay. It just will try to be as quick as possible. Sorry. Just okay. So I just want to explain to you the difference why the sequence differs. Okay. So why, although we use both of these algorithms are DFS, but the sequence they gave to us back are the sequences are different, right? So the first one, A, B, C, D, E, F. So this one that we just covered, like that I explained to you. So we go from A to B, then to C, then we go back to B to D to E to F. But iterative, what it does, it goes A, E, F, D, B, C. So A, E, F, D, B, C. And both of these are deep, so you go in depth. Why? The reason is simple. It just the reason is simple because if we use recursive solution, it checks the neighbors like from the first one to the last one. So it checks B, then it goes to E, then it checks E, right? But if we use iterative, it goes vice versa. So again, recursive, it checks neighbors this way. Iterative checks neighbors this way. And now probably you can understand what is the sequence, right? So why it is like this. So I hope it's clear, like, again, why? Because the sequence of like how these two different approaches check the neighbors are different, okay? So again, this way from left to right, this is recursive. From right to left, this is iterative, okay? Okay, great. And now, I hope it was clear. And now let's just talk about our final final thing, final concept I want to introduce you to, breadth first search. So again, breadth first search is very very close to the like kind of close to the depth first search, but they just use a little bit different concepts. So if depth first search, as we discussed earlier, it relies on a stack. Breadth first search relies on a queue. So that's the main difference. So here we have BFS. So visit neighbors at current depth first. So how it will be, it goes from A, then it goes to B, but instead of going deeper, it just checks neighbors at current depth first. So it checks E then, and then it goes C, and then it goes D, and then it checks, and then it goes for E, it checks the neighbor F, okay? So this is the sequence. Let's just go over it here. So again, start with an A, we mark it as visited, and we put it in our results array, okay? Then we go to B, we mark it as visited, and we put in our results array. Then instead of going deep again, breadth first search, it means check the neighbors on the same level first, okay? So B, and then where is it? Okay, and then we check E. So we push it in our results and we mark it as visited. Then we have C, right? And again, we push it in our results and mark it as visited. Then we check other neighbor of D or other neighbor of B, which is D. So we mark it as visited and we push in our results. And then the last one would be to check the neighbor of E, which is F. Okay, and we mark it as visited and we are done. Okay, so that's it. Essentially, again, unfortunately, cannot explain to you in a lot of details, but this is essentially a pseudocode. Again, if you want to understand it more in depth, just check this pseudocode. Again, we have code on GitHub, so you should be good. So just, I will just show you the code. So we have breadth first search implementation is very close to depth first search iterative implementation. But instead of using a stack, we use a queue. Again, we imitate queue using an array. You can create your own queue data structure instead. So, and we say, what do we say? Again, we do the same stuff here. Again, instead of just stack, we have queue, and then visited results, and then visited start, its start is true, and then while stack is not empty here, in breadth first search, we again rely on queue. So while queue is not empty, we just remove the first element in the queue. Okay, so shift again, since we kind of imitate the queue, we need to use a shift method on an array. But if you implemented your own queue data structure, you can use like queue to queue method, right? Instead, so to remove the first element in the queue, and then add vertex to the results array, so it's here, and then we just for each vertex not visited neighbor, we add it to the queue and label this vertex as visited. Okay, so if the neighbor of that vertex is not visited yet, we we add it to the queue and we mark it as visited, and we return the result. If I go here and call the BFS instead, so I just call BFS. And this is the sequence we get. So A, B, E, C, D, F. A, B, E, C, D, E. A, B, E, C, D, F. So that's essentially it. Again, very important to understand, like the DFS iterative and BFS almost identical. DFS relies on a stack. BFS relies on a queue. Very important to remember. And that's essentially it. Again, just read the pseudocode that we provided here on the slides. Again, go to the GitHub, and there, let me just, for a second, where is this? It's here. Okay. Oh, no, it's not here. I'm just trying to find the link for this repository.
The link to the repo, I will link it. It's a couple of times I've pasted in the chat, and it's also, I'll link it on the screen a bit later as well. But yeah, definitely check out the repo, and you can...
Andre, can you please put this here in our chat? This thing, I just want to show a couple of things. Yeah, if it's possible.
For sure.
Yeah, thank you. Okay. So yeah, that's essentially it. So now I just want to show you some things on the GitHub. Okay, so that's it. So this one is the repo for all the algorithms and data structure event series. So you have here again events, video, and slides. So again, you will be able to see everything. So if I go here, you will be able to see like slides for event 1. Okay, so, and then even the slides for this event are already here. So, okay, and then videos. So it's like the links to these recordings, then some resources for you to learn and practice. So again, if you want to study it more by yourself, so just open the slides. There you'll be able to find the pseudocode. So if I go here, yeah, so pseudocode here, and you will just go graphs, and then traversals, and there you have all the implementations. Okay, so DFS recursive, then iterative, and then BFS, and essentially this is the code for your graph to create it. Okay, so that's essentially it. thank you so much for your attention. Now, this is the turn for your questions.
Perfect. Thank you so much. We'll take just one until we wrap up. We went way over time with this session, and it's actually interesting because we can talk about these things for quite a while, right? So yeah, a while ago, Raf was asking also in which situations you would use BFS over DFS, right? What is the use cases for them, and why would you use one over the other? Alexander, do you want to answer that, or should I take it?
So I will not be so specific, but I do remember that some like pathfinding algorithms, like they can use a different way. So it's like either BFS or DFS. So different algorithms you rely on different on DFS or BFS. Then, to be honest, like it's better to do research on this topic because I'm not sure. Like, obviously there are some differences, right? Again, as we discussed, like some algorithms like topological sort, DFS, then what else?
Yeah, there's basically different kinds of properties that you want to look for in your graph, and you would use one algorithm over the other. It also depends on like what the sequence of your traversal you want to achieve. With DFS, you would go like as deep as possible. Maybe you want to like find the depth of the graph or something like that. I don't know. With BFS, it's like analyzing its spreads through your graph one layer at a time. Like we've seen that in the implementation, it will analyze one layer of neighbors first, then the second layer, and so on. So basically, really depends on your use case, and you definitely like do some research, see which one suits best for you. I will say that like most often DFS is used, although like for example the Dijkstra's algorithm to find the shortest path between two edges, it's very, very similar to BFS. So we're analyzing nodes in some particular order.
Mm-hmm. Can you please share for a second my screen? I just want to show something.
Yep.
Yeah, so this is a website called Visualalgo. So it essentially has a bunch of different, like, if you want to learn data structures, like I use it for myself because it's like easier to understand how different data structures work. So just check it out. It essentially has like, again, we talked about sorting last session. This session we talk like about graph traversal. See here? So like you should read the instructions how to use it, but essentially, if I just go like, you see topological sort, depth first search, breadth first search, if I go with starting with 0, it even gives you a walkthrough. So like, I mean, it's very, like it's nice website. So for you kind of to wrap your head around different concepts. And I believe like visualizations are obviously very like more intuitive than just words. So yeah, check this website out. Like I do recommend it. Actually, we should add it probably to our resources page on GitHub. So some people.
Yeah, we'll do that.
Okay, so that's it.
All right, I think that's everything that we have for you today. Yeah, if you have any questions, please feel free to join the Discord server. The link was shown a couple of times in this video and also in the chat. Feel free to drop by. We're always active on there. Ask some questions, and if you have anything else to add, actually, if you have ideas for next sessions, we would be more than welcome to hear those and discuss those. If you're interested in learning something more specific, we might think about creating another session and covering that. But for now, that concludes our series on data structures and algorithms. And yeah, I guess subscribe, and until next time.
Привет. Hello. Servus.
مرحبا.
Hola. Hello.
I'm inspired that there's so many people working to accomplish the same goal of creating a connected future.
By having students lead clubs on campus directly supported by Google developers, that's the best way to reach out to students.
It's really inspirational always to hear about members of the community who echo your values and echo your beliefs.
I've been listening more than I've been speaking, and I don't necessarily think that's a bad thing because I'm just getting all these ideas.
Google, it needs to reach a wider audience and be more relatable as a company, and I think Google is one of the brands that is very good at doing that.